Hi, welcome back to another exciting lecture on elementary functions, Math 112. I'm Anne-Marie Harden, and I am your instructor. Remember that. I am in Pendleton, Oregon, on the Pendleton campus. You can always email me through the information on the Canvas course site, or you can call me, although email is probably better. All the information you need to get a hold of me is in the Canvas shell for this course, and I am here to help you. So about this point in the class, you may be having some questions. Please reach out either through the course forums or through email, and let's work together to get through this. You do have other people in this class with you as well, and so on those forums is how you connect with your classmates. Today we are going to talk about the first of our trigonometric functions. So I'm going to give you my screen. We are going to talk about two trigonometric functions called sine and cosine. And don't let this scare you if you've never heard of them before. I'm going to explain to you what they are. They are useful and they become our friends very quickly. So right away we're going to jump right into it. Let's think for a minute about a point on the circle. Any point, pick one, and we're going to talk about it in general. Let's go point x, y. Some point on the circle with coordinates x, y. Now, I want you to think about for a minute the length of this line from the center of the circle, in this case the origin, to that point. The length of that line is r, the radius of the circle. Okay. Now, right triangles are beautiful things. They are our friends, and we know how they behave. And remember back to earlier math classes, you will have learned and worked with the Pythagorean theorem. Okay. So if we can construct said right triangle from this point by just dropping a straight line down. Now I want you to think for a minute, what is the length of this line? Y. Yes. And then the base of the right triangle is, sorry, stupid thing. Okay, is this distance right here. This distance is x, right? So, hypotenuse is r. The short leg is, in this case, the short leg, I should say the horizontal leg is x. The vertical leg is y. I want to take a look at Desmos for a minute, as soon as I get my pen back to a mouse. Okay, remember Desmos, it's my favorite graphing tool. And I have set up, hopefully it'll open. Come on, yes, okay. The point I want to make here is this. So let's simplify this for a minute. I'm going to get rid of the big circle and that line. Actually, I'm just going to do it this way. I'm going to, okay. So now we've got a circle of radius 1, okay? Let's say I look at the point, let's say I make, so if my x is 1, obviously I'm clear down here. If my x is 0.5, well, there is an x of about 0.5. Yes? What I want you to notice is I move my point along my circle, my x and y coordinates change. So different points on the circle, and I'm staying in this coordinate because my this particular model breaks if I go outside of this quadrant, but you can do this in any quadrant of your circle. So you can do this over here and over here and over here. I'm just staying in the first quadrant to make life simple. So the lengths of these sides will change. And the lengths of these sides depend on the angle made between the radius and the x-axis. So back in my presentation here, we named this angle theta. That's this angle right here between the x-axis and the slanted line. The ratios of my vertical and horizontal lines, my x and my y, change as I move along the circle. Not a surprise, since the coordinates of my point are changing. Here's the thing that I want you to understand, and this is really important. Let's look at another bigger circle. Bigger circle, the point on my bigger circle is further out. So of course, my x-coordinate for that point, the length of my lower line is different, right? And the length of my vertical line is different, yes? But here's the thing. The ratio of those remains the same. So even though the absolute lengths are different, let me see if I can make Desmos give me the points. So for my little bitty circle, my little bitty triangle, my x-coordinate is 0.78, which means that the length of that line there is 0.78 units. For my big triangle, that length is 1.56, so they're different. Likewise, my vertical for my little triangle is 0.626 units. My vertical for my big one is 1.25. But if I were to look at the ratio, if I were to take 0.78 and divide it by 0.626, it would be the same as 1.56 divided by 1.25. So these are similar triangles. Here's another way of checking that real quick. My little circle has got radius 1. My big circle has got radius 2. So that means that the ratio of my horizontal line to my radius should be the same. So let's set my x-coordinate in my little circle at 0.75, because that's easy. So my x, the length of my horizontal line, my x-coordinate, that's 0.75 divided by my radius, which is 1, is 0.75. The radius on my big circle is 2. So that means that my x-coordinate on my big circle should be, if I'm telling you the truth, and these things stay proportional, then this x-coordinate should be twice the x-coordinate on my little one. And sure enough, the x-coordinate for the point on my big circle is 1.5. If I change my radius to 3, and zoom out a little, sorry, I'm on an unfamiliar laptop. Ah, that's not what I want. Okay, sorry, it's all squishy. Let's see. Okay. Ah, let me go back to Desmos. About this time you're rolling your eyes in your head thinking, you've got to be kidding me. Okay, sorry. I don't want to leave. Go away. Okay, done. All right, let me see if I can make this look not quite so ugly. Now that was worse. Okay, we're getting somewhere. Better. Almost square. We're going to go with this. Okay. So my radius is 3 times now. My radius of my outer circle is 3 times the radius of my inner circle. So my ratio between my horizontal line and my radius should be 3 times, or my x-coordinate should be 3 times my 0.75. Sure enough, 0.75 times 3 is 2.25. So what I want you to understand is that for different size circles, the side lengths will change, but they will still remain proportional to one another. The ratios of these side lengths will remain constant for any given angle. Now, obviously, they're going to change as the angle changes. And in fact, these ratios are functions of the angle. And that's what we're going to talk about here. These things are used so often and are so important that we give them special names. The sine function is the ratio of the y-coordinate to the radius, or sine of theta, S-I-N is the symbol. It's the name of the function we call sine. That is the length of this vertical side divided by the length of the radius. This is true for any angle. Sine function is defined based on a right triangle. For a right triangle, if your angle of interest, in this case our theta, is any angle not the right angle, then the sine of this angle theta is equal to the side opposite the angle divided by the radius. Or in terms of our circle, the sine of the angle theta is equal to the y-coordinate of the point divided by the radius of the circle. The cosine is equal to the x-coordinate divided by the radius. Here's the other way we can think of this. For any point on a circle, given an angle and the radius that goes to the edge of the circle, so given an angle, the x-coordinate will be found from the radius multiplied by the cosine of the angle. The y-coordinate is the radius times the sine of the angle. Okay, trust me for now. I know this seems a little strange. Sine and cosine are just functions of the angle of inclination of the line that intersects the edge of the circle at the point xy. The length of this line segment will always be the radius of the circle. And we can express the x-coordinate as a function of this angle and this radius. And that x-coordinate is given by the radius of the circle multiplied by the cosine of the angle. And your calculator can take cosines for you. Okay? Calculator can also take sine. I will point you to some helpful sources for that if you have troubles. Just shoot me an email. If you don't know how to use your calculator, ask me and I will help you work through it. The y-coordinate is also a function of the angle, and it is given by the radius multiplied by the sine of the angle theta. Now we can use these definitions either way. We can use them to find the x or y coordinates, or we can use the x and y coordinates and the radius to find the cosine or sine of the angle. Okay. So let's work through an example. We've got a point 3, 4 on the circle of radius 5 at some angle theta, and we want to find the cosine of sine of the angle. Now notice we're not trying to find the angle. We just want to find the sine and cosine. What do we know? Well, let's write down on this circle what we know. We know the length of the radius is 5. We know that the x-coordinate is 3, which means that this length here is 3. And we know that the y-coordinate is 4, so the length of the vertical side is 4. The other way we can do this is we can just write r equals 5. Our point is at the coordinates 3, 4, so x equals 3, y equals 4. Remember that sine, the sine of any angle, is equal to x over r. Plug in what we know. The sine of the angle then is 3, because our x is 3, divided by the radius, which is 5. So our sine of our angle is 3/5. The cosine of the angle is similarly equal to the y coordinate of the point divided by the radius, or 4/5. Okay? All right. Now, we can also use our circle to find the sine or cosine of an angle. In this case, we want to find the sine and cosine of the angle pi over 2. You remember from the last lecture that pi over 2 is 1/4 of the way around the circle. So in radians, we're working in radians now. So this, okay, getting back my laser pointer. So our point where, so we started our x-axis, we move out along the circle pi over 2 radians, and we get to that point right there. That point is on the y-axis. Happens to be the one of the y-intercepts of the circle, right? So remember that for any point on the y-axis, the x-coordinate is 0. We know the length of this line here is the radius of the circle, r. So the coordinates of that point are 0, r, right here. That means x is 0, y is r. So the cosine of the angle pi over 2 is 0 over r, or 0. The sine of that angle pi over 2 is y over r, which means it's 1, because r divided by itself is 1. So the sine of the angle pi over 2 is 1, and the cosine of the angle pi over 2 is 0. All right. One of the things we're going to do in this class is talk about trigonometric identities. And identities are just rules for relating things to one another. And I apologize, that symbol right there should be a theta. I'm not sure how that happened. But here's what we're going to do. This is, we're going to develop, this is kind of an example of a proof. We're going to develop something called the Pythagorean identity. And I'm going to give you the punchline. This right here is the Pythagorean identity. It's a very basic, important, fundamental trigonometric identity. If you memorize nothing else, all right, you have to memorize some other stuff. But this is one of the things you should memorize in this class. You need to know that the cosine of any angle squared and added to the sine squared of that same angle is 1. Oh my goodness, my slides are off. That is not a sine 2. That is a sine squared. I swear they didn't look this bad the last time I looked at them. Sorry, guys. That's a sine squared. So cosine squared plus sine squared equals 1. And here's why. Remember our Pythagorean theorem from earlier classes. This is a right triangle, right? This guy, we're talking about this right triangle, or one just like it. For any right triangle, the length of the short leg squared plus the length of the other leg squared equals the length of the hypotenuse squared. Where this triangle, the length of this side here is the x-coordinate. The length of this point. The length of the vertical line is the y-coordinate of that point, and the length of the hypotenuse is the radius of the circle. So that means that x squared plus y squared equals r squared. We've talked about this before when we developed the formula of a circle. But we also know that x is equal to r cosine theta, right? And y is equal to the radius of the circle times the sine of theta. So now we're going to square that. We get r cosine theta squared plus r sine theta squared. Goodness. To make life easier, we could do this with algebra, but to make life easier, we're just going to choose a number for the radius, which is 1. This will work for any radius. And we do that, and we get that, sure enough, the cosine squared plus the sine squared of any angle is 1. Here's an example of how we can use that. If we know that the cosine of an angle is 5/8, we can use that information together with this theorem to find the sine of the angle. So here is the identity written correctly. The sine squared of theta equals the cosine squared of theta. This is just a shorthand way of saying sine of theta squared. We know the cosine is 5/8. We square that and do a little algebra, and we eventually get to the sine of the angle theta is square root of 39/8. I just did a little algebra and a little arithmetic there. We are not going to put in a decimal approximation for the square root of 39. We're going to leave it as the square root of 39. The 8 came from the square root of 64, which is the denominator of the fraction, and so therefore will be the least common denominator of this arithmetic step. Okay, if you have trouble with that, with the operations I have out here, please get a hold of me and I'll walk you through it, okay? Let's now, sine and cosine, sine of an angle and the cosine of an angle are symmetrical. Here's what I mean by that. Let's look at, so consider this angle, whatever this guy is. That is some angle, theta. Now, if you remember your geometry at all, that means that this angle is also that theta. And I set this up so that this angle is the same, and that means this angle is also the same. Now, let's think about this. This is some point x, y. Okay? So what's the coordinate of this point over here? It's negative x, y, right? And this one down here is that negative x, negative y. And this one over here is x, negative y. What's that mean for sine and cosine? Well, remember that the cosine of the angle is the ratio of the x to the radius, right? So for this angle and this angle, they have the same y coordinates. So the sine of those two angles is going to be the same. Now, you may say to yourself, but wait a minute. We don't measure angles from the negative x-axis. You're right, we don't. What that means is the sine of this angle, that I will call alpha, is the same as the sine of my original angle, theta. Now I got from theta to alpha just by adding 90 degrees. Okay? So if you move around a circle by 90 degrees, your sine is unchanged, and your cosine will have the same absolute value but opposite sign. It'll be negative, right? So you can kind of see what's going on here. Let's play with this for a minute. I'm going to go back to Desmos. I'm actually going to go all the way back out to Desmos homepage. And I'm going to go in here to some math examples, and we're going to look at this. So this is a video. Well, it's an animated graph. I'm going to put it on projector mode so you can see it more clearly. And I did not create this. I'm just borrowing somebody else's. So here's what this thing's going to do. I am going to reset it to 0. So what I want you to understand, I'm going to show you what's going on here. First of all, notice that the x-axis is in radians. Okay? So this is pi over 3, 2 pi over 3, pi, 4 pi over 3. We do this sometimes with trigonometric functions. What we're going to do is we are going to move around the circle. And what is happening here is that the cosine of the angle, the sine of the angle is being graphed in the blue. So right now I'm at an angle of just a little bit more than pi over 2. And remember, we looked at this earlier, that the sine of pi over 2 is 1. So right here is about 0 pi over 2. Right here, my sine of that angle is 1. Okay? If I go all the way out to an angle of pi, which would put me right there on the x-axis, the sine of that angle is 0. All right. Let's keep going. Move my picture here, see if I can get, there we go, I can zoom out. Okay, so let's keep going around our circle. What's going to happen when I go to the negative, or all the way down to the y-axis? So I'm going to keep going. So here my angle is actually, so I went pi and then another half pi, so this is 3 pi over 2. We think about what I said a minute ago about the symmetry. We would expect my sine to be the opposite of the sine at this point. And sure enough, so the sine is the y-coordinate, which is -1. If I keep going on around my circle, whoops, I went too far. You can see that I have made a full, complete pattern, right? I've come back to 0. Now, here's the thing to understand. At this point where so this symmetry holds all the way around the circle. And if I keep going, I'm just going to keep building the same pattern over and over again. Sine is what we call, the sine function is what we call a periodic function. So there are 4 angles around the circle that will have a sine that is the same in magnitude, and the numeric signs of the sine function, positive or negative, will alternate as we go around the circle. The same thing is true for the cosine. Now remember that the sine of an angle is related to the y-coordinate, and the cosine of the angle is related to the x-coordinate. So in the first quadrant, where both x and y axes are positive, both sine and cosine will be positive. In the second quadrant, where our x values are negative, and our y values are positive, the sines of the angles will be positive and the cosines will be negative. And we can continue that pattern all the way around. Angles that differ by 90 degrees will have the same absolute value in sine and cosine, but they will be potentially the cosines will be opposite in sense, positive or negative. The sines will be the same. Play with that a little bit. Work through some, try it with you on your calculator. Take some sines and cosines. Make sure this makes sense to you. Okay, so the points on a circle. These are the same familiar angles that we've talked about before. This is a very important graphic for you to wrap your brain around. Remember that all of the points on a circle will have coordinates of r cosine theta, comma sine, r sine theta. So the x-coordinate can always be found by taking r times the angle that forms that point times the cosine of that angle, and the y-coordinate is r times the sine of that angle. Notice that a lot of our values have square roots in them. If you think about where these come from, that will not surprise you because a lot of them come from the Pythagorean theorem. There are some of these values that you want to memorize. You want to know that the cosine of 30 degrees is the square root of 3 over 2, and that the sine of 30 degrees is 1/2. You want to know that the cosine, you want to know the cosine and sine of pi over 6. So what you need to know, what you need to actually be able to regurgitate is the sine and cosine of these angles. 0, pi over 6, pi over 4, pi over 3, and pi over 2. You actually need to be able to do that for 2 pi over 3, 3 pi over 4, and 5 pi over 6. But if you understand the relationship as we move around the circle, then you only need to memorize these 5 points, and then you can get to the others by changing the sign as necessary. The sign is in the positive or minus sign. So if this is confusing to you, be sure you ask me some questions because this is absolutely critical that you understand. And I know that I may not be making any sense, but without you in front of me to ask me questions, I cannot. I need you to ask me questions so that I don't just repeat myself and end up confusing you more. So please, if you're having troubles with this, let's schedule a time to get together and work through this in a conversation. Now let's look at an example. I've been telling you how useful this is. Let's actually look at an example. We've got a boat that's detected by a radar station. And it's detected 8 miles away at an angle at 70 degrees north of east. How many miles northeast of the radar station is this boat located? So here's what we have. Radar goes out in a circle. So we set a coordinate system and we put our radar station at the center of our circle. We know that our boat is 70 degrees north of east. So my positive x-axis is east, my positive y-axis is north. So I draw a line that is inclined at 70 degrees. And this point right out here is where the boat is. How do I find that? Well, I take out my calculator because I know that the x-coordinate of that point is equal to the radius times the cosine of my angle of inclination. And the y-coordinate of that point is equal to the radius times the sine of that angle of inclination. So I take out my calculator and I plug in 8 times the cosine of 70 degrees. My calculator will tell me that the cosine of 70 degrees is 0.34. I multiply that by 8, and I get 2.7 miles. That is how far east of my radar station that boat is located. I do the same thing for the sine, and I find that my boat is 7.52 miles north. Okay. So what do you need to know from this? You need to know the definition of sine and cosine in terms of the x-coordinate of a point and the radius of the circle. You need to know that or the y-coordinate of the point and the radius of the circle. So you need to know that the cosine of an angle is x, the x-coordinate of the point divided by the radius, and that the sine of the angle is y over r. You need to know that the x-coordinate of any point on a circle can be found by taking the radius of that circle and multiplying by the cosine of the angle that will form that point on the circle. I hope that makes sense. And you need to know that the y-coordinate is related to the sine of the angle in the same way. You need to know that the cosine of any angle squared plus the sine of that angle squared is equal to 1. Those are the things you need to know, and you need to be able to apply those things in order to solve problems like this one that's on the screen. Okay, big deep breaths. Take a look at the textbook. Take a look at some of the other videos that are included in the Canvas shell. And email me if you have any questions. Reach out on the forums. I'll talk to you all again soon.